Hello to everyone watching. My name is Gabriel, and I would like to introduce to you the massive algorithm for tractable and robust Bayesian learning of many-dimensional instrumental variable models. This is joint work with my co-authors at Radboud University, Tom Claassen and Tom Heskes. In many fields, such as the medical sciences, we are interested in estimating the causal effect of an exposure to, let's say, alcohol consumption on the risk of developing a disease such as coronary heart disease. This estimation is not directly possible, however, due to the presence of unmeasured confounding. Now, the traditional clinical way for handling these confounding effects would be to perform a randomized control trial. Such a trial would be unethical in this case, since it would involve prescribing alcohol, which has well-known damaging effects. One alternative method that has gained a lot of traction in the medical sciences in the past 20 years and relies only on observational data is Mendelian Randomization, or MR. The idea here is to use a genetic variant to define separate groups that differ in their level of exposure. In our example, we know that the ALDH2 gene is involved in alcohol metabolism. People inheriting one particular variant of this gene will experience unpleasant side effects such as flushing or dizziness when consuming alcohol. As a result, they are naturally inclined to consume less alcohol compared to people possessing other gene variants. We can therefore use this gene as an instrumental variable, or IV, for causal effect estimation. Like all instrumental variables, genetic variants have to satisfy a particular set of causal assumptions which are encoded in this causal graph. One of these causal assumptions is that the genetic variant is related to the outcome only through its effect on the exposure. This assumption is unfortunately unlikely to be satisfied in general, since many genetic variants exhibit pleiotropy, meaning they affect multiple observable traits or phenotypes. For example, ALDH2 also has a reported correlation with tobacco consumption, which then influences the risk of developing coronary heart disease. If the genetic variant is related to the disease outcome via multiple pathways, then the IV estimate will be biased. This is a problem particularly when using genetic variants whose biological function is unknown or poorly understood. Even if a number of IV estimates for different genetic variants seem to agree with each other, we cannot be sure whether these are valid instruments or whether these exhibit similar pleiotropic effects. We have to somehow account for this model uncertainty. We propose to handle the issue in a more robust manner by considering large sets of candidate instruments. We start by assuming a more general model where each potential instrument G may have a pleiotropic effect, denoted here by alpha. We want to estimate the causal effect of the exposure X on the outcome Y, denoted by beta. To do this, we assume a conditional linear Gaussian distribution on the exposure and outcome given the genetic variance. In order to automatically select the candidate genetic variants that are more likely to be valid instrumental variables, we put a shrinkage prior on the pleiotropic effects. For this purpose, we have chosen a simple and intuitive Gaussian scale mixture with two components. This is a soft spike and slab type prior where the spike component shrinks parameters much more strongly than the slab component. With this mixture prior, we distinguish between pleiotropic effects that are strong or relevant, which would correspond to invalid instruments, and those that are weak or close to zero, which would correspond to valid instruments. Given the uncertainty in instrumental variable selection, we propose to compute a Bayesian average solution over the possible IV models. We define an IV model as given by a particular combination of lane variables iota, indicating whether each pleiotropic effect is in the spike or slab component. This way, we encourage sparse solutions through selective shrinkage, whereby pleiotropic effects are shrunk down to zero unless there is significant evidence in the data for the presence of pleiotropy. Naturally, we cannot efficiently explore the entire exponential model space, but instead propose to average over a small set of promising IV models. For each IV model, we then need to compute the parameter posterior and the model posterior. The parameter posterior surface is relatively simple, as can be seen in this example projection surface. We have observed empirically, and we conjecture that there are no more than 5 different local optima or modes for each IV model. We can therefore achieve a fast approximation of the parameter posterior using Laplaces Method. More specifically, we devise a smart procedure of finding these optima by running a standard optimization routine from a small number of carefully chosen starting points. We perform a Laplace approximation for each distinct optimum found. We then combine the results to obtain the parameter posterior as a mixture of Laplace approximations. Moreover, by evaluating and summing up the normalization constant of each approximation, we can also arrive at a reasonable estimate for the model evidence. We still need a way to explore the model space efficiently. We have proposed to use a stochastic search approach called Markov Chain Monte Carlo Model Composition, or MCQ. This procedure essentially consists of metropolis steps in the IV model space, where at each step we propose a new IV model from a neighborhood of the current model and determine if it should be our next sample based on this acceptance ratio. For simplicity, we assume a uniform prior over the model space, so then the differences between models is given by the marginal likelihood or model evidence, which is the normalization constant of the parameter posterior given that particular IV model. To sum up, our massive algorithm has two main ingredients: model assessment using a mixture of Laplace approximation and stochastic search using MCMC model composition. The end goal of our algorithm is a robust and accurate instrumental variable estimation when we do not know a priori which candidate instruments are valid. Our algorithm is provably effective in real-world applications. While we design our algorithm with Mendelian randomization applications in mind, it can be equally applied to any kind of instrumental variable analysis. One example of MR application involves the effect of body mass index, an obesity measure, on the risk of developing psoriasis, a common inflammatory skin disease, pictured here. An MR analysis was designed in which 97 variants were used as genetic instruments for estimating the causal effect of BMI on psoriasis risk. In this example, the genetic variants were carefully selected based on their robust association with BMI found through large genome-wide association studies. We ran the massive algorithm on the many instrument problem and obtained a similar but more complete description of the causal effect estimate. For comparison, we showed the classic frequentist MR estimate together with its confidence bounds. Interestingly, the output of our algorithm suggests that only 2 of the genetic variants are strongly pleiotropic, which also explains why the results are similar for this particular example. Note that in the original analysis, there was little evidence found for the presence of pleiotropy, but with our approach, we could pinpoint which few variants could exhibit significant pleiotropic effects. To conclude, we have emphasized the importance of taking model uncertainty into account in many instrument MR applications. A well-established principal solution of assessing and incorporating model uncertainty is to perform Bayesian model averaging over the space of possible models. Such an approach is generally intractable due to the size of the model space and the complexity of arbitrary posteriors. To solve the first issue, we derived the fast approximation to our proposed parameter posterior based on a mixture of Laplace approximation. To solve the second issue, we propose to explore the model space more efficiently using an MCMC stochastic search approach. By combining these two ingredients, we have arrived at a tractable, fully Bayesian algorithm that outputs a complete description of both the parameter and model uncertainty. We can simply plug data on hundreds of genetic variants into our massive algorithm and get a reliable estimate in a reasonable amount of time without knowing in advance which of these are valid instruments. Thank you for your attention.